Hello, hello, hello. It is I, Gustav Kirchhoff, here with Physics 2, Lab 4, where we are going to be measuring the voltage drop qualitatively across resistors in a DC circuit, and also determining the time constant of an RC circuit by plotting the discharge of a capacitor over time. And in order to do this, we are going to be using the node rule and the loop rule. The node rule is essentially a statement of conservation of charge. It says that the current going in to any node on a circuit must ultimately equal out to zero with the current coming out. And it also the loop rule is essentially a conservation of energy statement that comes out of the fact that electric fields are path independent, meaning that any closed loop that you draw within a circuit must have a net voltage change of zero. And so using these two, we can make predictions about easily about what simple circuits are going to do. So in this lab, we used an online program to simulate different circuits, and in these cases, the system was the circuit that we made out of batteries, light bulbs, resistors, capacitors, and wires, whatever was being used. And the surroundings would be essentially nothing but perhaps these voltmeters or ammeters that we use to determine current and voltage. In this case, the initial states of the systems varied. Sometimes it was with charged capacitors, sometimes it was with uncharged capacitors. Now, for the first part of this lab, I qualitatively determined the change in voltage, the voltage drop using a voltmeter, and created this graph, which is not exact, but it does demonstrate the fact that the voltage drop across the 100 ohm resistor is much greater than the voltage drop across the 47 ohm resistor, and that these voltage drops could be approximately calculated by the resistances of those resistors, and they do match up with Ohm's law. In the second part of this lab, we determined the time constant of an RC circuit by measuring how much voltage was running across a resistor over time and plotting that. And we get the slope of the natural log of that graph is 0.492, very close to 0.5. Doing some math on that, we've determined the time constant to be about 2, and this is the time where we would expect the voltage to be 1 over E, what it initially was, and that does match up with observation. And of course, we are approximating the systems here as ideal, so the wires have no resistances, and also what has no resistances are the ammeters in these simulations. And in reality, real ammeters have some small resistance, so they do affect the circuit that is being tested, but it's meant to be as small as possible so as to minimize that effect. But our simulated ammeters have no resistance, so that is a fairly large difference between a simulated ammeter and a real-life ammeter. For the second what-if question, when in simulation and when in purely theoretical systems, if the resistance is equal to 0, then the time constant would also be equal to 0, and we would calculate that the charge time of a capacitor when just hooked directly up to a battery with no resistance would be instant. There would be 0 time between no charge and full charge. But in reality, we're just approximating these wires as having no resistance, and no wires truly have no resistance. So the true resistance of the system can never be 0, and thus the capacitor can never charge instantly. It would just charge very quickly because of that low resistance. Thank you.